Relative motion. Here's our order of how we'll get through this lesson. Some takeaways in the forms of objectives that you will know by the end of this lesson. Describe the reference frame of a given observer. Describe the motion of objects as measured by the observers in different inertial reference frames. To understand those objectives, we need some fundamental knowledge. First of all, the choice of reference frame will determine the direction and magnitude of quantities measured by an observer in that reference frame. Measurements from a given reference frame may be converted to measurements from another reference frame. The observed velocity of an object results from the combination of the object's velocity and the velocity of the observer's reference frame. Combining the motion of an object and the motion of an observer in a given reference frame involves the addition or subtraction of vectors. And finally, the acceleration of any object is the same as measured from all inertial reference frames. Our vocabulary: a frame of reference is a set of coordinates used to describe the motion of objects. It defines the point from which measurements are made. Inertial means not accelerating, which could be constant velocity, or it could be stationary. Vector addition: the combining of vector quantities using graphical or algebraic methods. Vector subtraction is the combining of vector quantities using graphical or algebraic methods with one vector pointed in the anti-parallel direction. Relative velocity is the observed velocity, or an apparent velocity, of an object resulting from the combination of the object's velocity and the velocity of the observer's reference frame. Anti-parallel means exactly opposite direction. Magnitude and direction. The choice of reference frame determines both the magnitude and direction of the quantities measured. The easiest way to go through this and understand it is by looking at it in action. So I've got the little cartoon here. Example: if Chris is on a moving train and measures the speed of Sam in a passing car, their measurement will differ from that of someone standing still by the side of the road. To us, the observer in an inertial frame of reference, or not moving frame of reference, or the earth frame, as it's sometimes known, Chris, who's on the train, is traveling at 15 meters per second. Sam, who's in the car, is traveling at 10 meters per second. We are not moving, so we're moving at 0 meters per second. Now let's go ahead and think about Chris's frame of reference. So this is to Chris. So everything is relative to Chris. Chris is traveling at 0 meters per second. You notice this when you're in the car. Even though your car is moving, if you look at things inside of your car, because they're in your frame of reference, they're moving with you, it appears like they're not moving. We're going to see that in action a little bit later. Meanwhile, Sam is traveling at -5 meters per second. They're both going in the same direction, but because Chris is traveling faster in the train, Sam in the car appears to be moving backwards. Same with us. We are moving backwards relative to Chris, -15 meters per second. An equation for this would be your relative velocity, or here it has your apparent velocity, equals the velocity of the object that you're trying to figure out, minus the velocity of the observer's frame of reference. For Sam, relative to Chris's frame of reference, his relative velocity is going to be 10 minus 15, which is -5 meters per second. So Sam being the object we're looking at, and Chris's frame of reference being the velocity that we're using for the frame of reference, we get the relative velocity of -5 meters per second. Now let's go into Sam's frame of reference. Chris is now traveling at 5 meters per second. Sam is not traveling, just at 0 meters per second. And we are moving -10 meters per second. Again, you can go through this equation, but that is not right. If an object is going in the opposite direction, we can subtract the vectors. Example: if you're on a boat, or a shell, as it's known, traveling at 15 meters per second eastward and see an oncoming black shell moving at 15 meters per second westward relative to the shore, what is the black shell's velocity relative to you in the white shell? So we see the vectors. We have the gray vector representing the black boat and the white shell being represented by the white vector. We are subtracting these two because they're in the opposite directions. So whenever we subtract vectors, we're going to add the anti-parallel. That's it. So we started with negative 15 meters per second because it's 15 meters per second to the left. Then the anti-parallel, negative 15 meters per second, that gives us a relative velocity of negative 30 meters per second. If that doesn't make sense to you, look at it mathematically. There we go. So we have a negative minus a positive. How do we deal with a negative minus a positive? We add a negative. If an object is going in the same direction, we can add vectors. Let's say you are on a blue shell traveling at 5 meters per second eastward and see a black shell moving at negative 1 meter per second relative to you. What is the black shell's velocity relative to the shore? Right, 4 meters per second. One thing about this video taken from the Bolles School crew, thank you to Eric Lansaw. In the top left corner, you see the camera fixed on the boat. It does not appear like that young man rowing is going anywhere. Meanwhile, there's the overhead view that shows clearly not only are they moving, but they're overtaking the black shell. If an object is moving at the same velocity relative to you, it's going to appear like it's not moving. Like here. So this, I know it is a loop, but you can get this idea. And this really is one of the cool experiences whenever you're walking at the same speed as somebody and looking at them. Everything else in the background is just blurring by. You two are seemingly moving at the same speed, and neither one of you look like you're moving to each other. This also happens in the car often. You might be in a parking lot and staring down at your phone, and a truck parked next to you starts backing up, and then all of a sudden you jump up because it feels like you're moving forward, because the car's moving backwards. And your brain already knows this physics, and it kind of does all of this for you, and it alerts you, hey, something weird's happening. All right, worked example. Imagine two cars, car A and car B, traveling on a highway. Car A is moving at a constant speed of 60 meters per second in the westward direction, and car B is moving at a constant speed of 80 meters per second in the westward direction. You want to calculate and compare car B's speed and car A's reference frame. So we're going to use that same equation, our relative velocity of B relative to A equals the velocity of B minus the velocity of A, which gives us the relative velocity of negative 20 meters per second. Relative velocity is the observed velocity of an object resulting from the combination of the object's velocity and the velocity of the observer's reference frame. For example, if you're on a train traveling at 10 meters per second eastward and throw a ball forward at 5 meters per second, the ball's velocity relative to someone on the ground is the vector sum of the train's velocity and the ball's velocity. Here we have the train's velocity of 10 meters per second to the right and the ball's velocity 5 meters per second to the right. We're just going to add up these two vectors. 10 plus 5 will give the apparent velocity, or the relative velocity, relative to the observer of 15 meters per second. This is called the tip-to-tail method of adding vectors. We can move the vector anywhere as long as we don't change the direction. So when I did this, notice how the vector does not change the angle that it's pointed at. That means the direction is not changing. Next steps, complete practice problems. There's your AI prompt. You can pause the video to copy it.